From the deepest cosmic voids to the brightest galactic cores, the universe hums with an ancient, powerful rhythm. It is the song of creation, destruction, and rebirth, played out across unimaginable scales of space and time. What forces sculpt the cosmos? What destinies await the celestial giants that illuminate our night? How do these distant, burning spheres dictate the very elements that form our world, and indeed, ourselves? Prepare to journey into the heart of stellar evolution. Witness the birth of light, the fiery dance of life, and the spectacular end of stars. Our story begins in the vast, cold emptiness between the stars, within colossal clouds of gas and dust known as nebulae. These cosmic nurseries are the crucibles where future suns are forged. Here, gravity begins its relentless work. Tiny fluctuations in density, perhaps triggered by a passing supernova shockwave, cause pockets of gas to clump together. Over eons, these clumps grow, drawing in more material, slowly collapsing under their own increasing gravitational pull. As the cloud contracts, it spins faster, flattening into a disk with a dense, hot core at its center. This protostar, still shrouded in its dusty cocoon, is not yet a star. It is a nascent heart, warming to life. The pressure and temperature within this core continue to rise dramatically. Atoms collide with ever-increasing energy until a critical threshold is reached. At millions of degrees Celsius, a miraculous transformation occurs. Nuclear fusion ignites. Hydrogen atoms, under immense pressure, fuse to form helium, releasing an extraordinary burst of energy. This outward pressure perfectly balances the inward crush of gravity, and a star is born. With fusion burning steadily in its core, the star enters the longest and most stable phase of its life, the main sequence. Our own sun is a main sequence star, about halfway through this stage. During this period, the star shines brightly, converting hydrogen into helium, maintaining a delicate equilibrium. The star's mass at birth is the single most important factor determining its characteristics and lifespan. Massive stars burn through their fuel at an astonishing rate. They are hotter, brighter, and often blue-white in color, but their lives are tragically short, lasting only a few million years. Smaller stars, like red dwarfs, conserve their fuel, burning slowly and steadily for trillions of years, far longer than the current age of the universe. They are cool, dim, and red. Our sun, a yellow dwarf, represents a middle ground. It will shine for approximately 10 billion years, a cosmic lifetime that allows for the slow, intricate development of life on planets like Earth. As a star like our sun exhausts the hydrogen fuel in its core, the delicate balance is disrupted. Fusion slows, and gravity begins to win, causing the core to contract and heat up further. This increased core temperature ignites a shell of hydrogen fusion around the helium core. The outer layers of the star expand dramatically, cooling as they stretch into space. The star transforms into a red giant, hundreds of times its original size, its surface glowing with a cooler, reddish hue. It may even engulf its inner planets. Within the red giant's core, helium fusion eventually ignites, forming carbon and oxygen. This phase is often unstable, leading to pulsations and the expulsion of the star's outer layers into space. These ejected shells of gas and dust form beautiful, intricate structures known as planetary nebulae. They are not related to planets, but their round, colorful appearance reminded early astronomers of distant worlds. After shedding its outer layers, all that remains of a low-mass star is its incredibly dense, hot core. This is a white dwarf, a stellar remnant roughly the size of Earth. A white dwarf no longer undergoes nuclear fusion. It shines only by residual heat, slowly cooling over billions of years. Its matter is so compressed that a single teaspoon would weigh tons. The electrons within the white dwarf are packed so tightly that they resist further compression, a phenomenon known as electron degeneracy pressure. This force prevents the star from collapsing further. Eventually, after eons of cooling, a white dwarf is predicted to become a black dwarf, a cold, dark, theoretical object that no longer emits light or heat. However, the universe is not old enough for any black dwarfs to have formed yet. These stellar embers are the quiet, dignified end for the vast majority of stars in the cosmos, including our own sun. They are monuments to a life lived in fire, now fading into eternity. For stars far more massive than our sun, the end is anything but quiet. Their immense gravity drives their cores to much higher temperatures and pressures, enabling them to fuse heavier elements. After exhausting hydrogen, these giants fuse helium into carbon, then carbon into neon, oxygen, and silicon. Each stage is hotter and shorter-lived than the last, like a cosmic countdown. This process continues until the core is primarily iron. Iron fusion, unlike lighter elements, consumes energy rather than releasing it. This marks the star's ultimate crisis. With no outward energy pressure to counteract the crushing inward force of gravity, the iron core collapses in a fraction of a second. It implodes with unimaginable speed and power. The outer layers of the star, still undergoing fusion, rush inward, slamming into the now incredibly dense core. The rebound creates a shock wave of unparalleled destructive force. The shock wave rips through the star, blasting its outer layers into space in a cataclysmic explosion known as a supernova. For a brief period, a single supernova can outshine an entire galaxy. These explosions are the universe's primary factories for heavy elements. Elements heavier than iron, including gold, silver, and uranium, are forged in the extreme conditions of a supernova. The expanding cloud of gas and dust left behind by a supernova is called a supernova remnant. These beautiful, intricate structures enrich the interstellar medium with the building blocks for new stars and planets. The Crab Nebula is a famous example, the remnant of a supernova observed by Chinese astronomers in 1054 AD. At its heart lies a rapidly spinning, incredibly dense object. Supernovae are not just destructive, they are essential for life. Without these cosmic explosions, the universe would be a much simpler place, devoid of the complex elements necessary for planets and for us. What remains after a massive star's core collapses and explodes depends on its initial mass. If the core is between about 1.4 and 3 times the mass of our Sun, it forms a neutron star. During the core collapse, the immense pressure forces protons and electrons to combine, forming neutrons. The entire core becomes a giant atomic nucleus, incredibly dense and compact. A neutron star is typically only about 20 kilometers in diameter, yet it contains more mass than the Sun. A single teaspoon of neutron star material would weigh billions of tons. Many neutron stars spin incredibly rapidly, sometimes hundreds of times per second. Their powerful magnetic fields channel beams of radiation from their magnetic poles. If these beams sweep across Earth as the star rotates, we detect them as regular pulses of radio waves. These objects are known as pulsars, cosmic lighthouses signaling across the galaxy. If the collapsing core of a massive star exceeds roughly 3 times the mass of our Sun, even the immense pressure of degenerate neutrons cannot halt the gravitational collapse. The core continues to shrink, compressing itself into an infinitely small, infinitely dense point called a singularity. This creates a region of space-time where gravity is so extreme that nothing, not even light, can escape. This region is known as a black hole. Its boundary, the point of no return, is called the event horizon. Crossing this threshold means an irreversible journey into the unknown. Black holes are not cosmic vacuum cleaners, actively sucking in everything around them. They exert gravity just like any other massive object, but their extreme density makes their gravitational pull inescapable at close range. They are detected by their gravitational influence on nearby stars, or by the intense X-rays emitted by superheated gas spiraling into their event horizons. Black holes represent the most extreme and mysterious endpoint of stellar evolution. From the gentle glow of a nebula to the violent fury of a supernova, and from the quiet fading of a white dwarf to the enigmatic embrace of a black hole, the life cycle of stars is a testament to the universe's dynamic nature. Each stage is a crucial chapter in the cosmic story, shaping the very fabric of existence. The elements forged in stellar cores and scattered by supernovae are the building blocks of planets, moons, and all life. We are, quite literally, stardust, the carbon in our bodies, the oxygen we breathe, the iron in our blood. All were created in the hearts of ancient stars and dispersed across the cosmos in their spectacular deaths. The universe is a grand, interconnected tapestry, woven with the threads of stellar evolution. As we gaze upon the night sky, we are not just seeing distant points of light. We are witnessing the ongoing epic saga of creation and transformation. The journey of a star is a profound reminder of our place in the cosmos, a humbling and inspiring tale of immense power, intricate processes, and the enduring wonder of the universe.